So at this point in Chapter 7, we've covered centripetal acceleration, we've looked at Newton's law of universal gravitation, and we've gone over some scenarios with motion in space. Now we're moving along to look at torque. So a brief note about torque. It's not covered in a lot of high school physics classes up until AP Physics C, which is mechanics, but it is covered in this textbook. So I'm going to give a brief introduction, but if this is confusing and your teachers have told you to just think of forces as being applied to a point or to the center of an object, then you can skip this section on torque and move on to the next chapter. Torque is defined as the ability of a force to rotate an object around some axis. So the quantity of torque depends on both the distance of force from the axis and also, of course, the size of the force. So the distance from the axis of rotation to the force that's being applied is known as the lever arm. So we can visualize this if we have this wrench here. We have a force that's applied to the end, and its axis of rotation is over here around a bolt. And we're measuring the lever arm as the distance between them, which we'll call d. That'll be used later on when we're calculating torque. Torque is also affected by the angle of the force that's being applied. So we can write the entire equation as torque, which is expressed as this sort of swirly T, is equal to force times distance times sine theta, or the angle between the force and the object to which it's being applied. And the units of this equation, just to note, are newtons times meters, because this is force times distance. So here's another diagram just to show what the equation means. We have some force, F, that's being applied at an angle theta over a distance d from this axis of rotation. All of those variables come into play when we're writing the equation. And you can note that torque is a vector quantity, like most forces, and also that the sum of torque is calculated by adding F1 times d1, or the force and distance of the first force, plus the second force, plus the third force, and so on, depending on how many forces are applied to a certain object. Here are some practice problems for torque. Number 1. Find the magnitude of the torque produced by 3 newtons of force applied to a door at a perpendicular distance of 0.25 meters from the hinge. So we have this distance d of 0.25 meters, and then we have a force F, which is 3 newtons. Now we know that torque equals force times distance times the sine of the angle between them. In this case, the angle is 90 degrees because they've told us it's a perpendicular distance. So we can say that the sine of this is just 1. So we'll rewrite torque as just force times distance, and now we know both of those values. We have torque equals 3 times 0.25, or in other words, 0.75 Newton meters. Number 2. If the torque required to loosen a nut has a magnitude of 40 Newton meters, what minimum force must a mechanic exert at the end of a 30 centimeter wrench to loosen the nut? So first we're going to be careful with the units here. We have 30 centimeters, so I'm going to rewrite that right away as 0.3 meters because we have to keep that consistent because force is expressed in Newton meters. So now we're looking at torque. That's equal to force times distance. In this problem, we know the distance and we know the torque, and we're solving for force. So let me plug in the numbers we have. The torque is going to be 40 Newton meters. Force is what we're solving for, and finally it's at a distance of 0.3 meters. Now if we divide both sides by 0.3, we get that the minimum force that the mechanic needs to exert is going to be about 133 newtons. Our last review problem for torque, number 3. A cat pushes on a door with the same magnitude, which was 3 newtons, as in problem 1, but this time at an angle of 30 degrees with the door. What is the new magnitude of the torque that's produced? So this time, instead of having a perpendicular force applied to the surface of the object, we're going to have a force that's at an angle, as you can see, and that angle is going to be 30 degrees. So this time, we'll need to write torque as force times distance times sine of theta. We're solving for torque. We know that the force is 3 newtons. The distance is going to be 0.25 meters. We got that from problem 1. And then we're going to do sine 30 degrees because that's the angle. Now if we simplify this, torque equals 0.75 times, and then the sine of 30 is 0.5. We multiply that out to get 0.375 Newton meters. At this point in Chapter 7, we've gone over situations with centripetal acceleration and circular motion. We've also looked at some gravitational examples, and then finally I've given a brief introduction to torque that will come in handy later on in AP Physics if you are watching this ahead of time. Thank you for watching.